we can write as follows. And we can again expand for each of them as in the denominator as like this, similar to the above notion. And we finally get a formula for the Bayes theorem, for a general Bayes theorem of n events. Um, and yeah, so now like I've maybe we can come to this question a bit later. I think I will be at the end like sharing some questions on probability. If there are some of you that are new and not much sort of like good at probability skills and all, so I would share those things at the end of the lecture. So maybe you can come to this a bit later. So we'll define the notion of independent events first. Two events, E1 and E2 are independent if the joint distribution is actually, I can write it as a product of two events, probability of two events. And as we discuss also this exact thing, the joint distribution can also be written as P of, it actually basically means the same. The notation wise is the E1 intersection E2. So this is what we also discussed at the top, where we had P of y equal to P of xy is basically P of y equal to P of x or y. And so x is here is a, y is my all the bi's, and I all summation over all the bi, and I just do x comma bi, and there's the same in similar notion. There's the same that holds, and so this is actually a very simple notion of how we define independence between two events. And then the other thing is like if I have n events now, if I define it for general n events, then it's basically a product of all the probabilities of the corresponding events in itself. So yeah. Now now what we'll be discussing next is mostly on distribution functions, like what we mean by probability density function, cumulative distributive function, and some notions of statistical measures like expectation variance and covariance and all. And just a moment. Yeah. But yeah, so uh, let's first discuss about in terms of like what do we mean by probability in itself. So in ML models also, like when we are building a ML model, often there would be like things like called prediction that we want to make for a model on a new data set, for example. And the prediction it basically means there is a notion of uncertainty in there, like how certain you are that this model will predict this thing, or the other class, for example, in a classification task. And that uncertainty it's in itself is it's something of a measure that we want to sort of like um, give a sort of like a mathematical measure through probability. And that's the notion. And so probability theory, as Laplace had mentioned, probability theory is nothing but common sense reduced to calculation. So it's basically like it's the notion of uncertainty, but it's more rigorous on like something we can measure, quantitative measure that you can put into. So I'll just go through a brief of the notations because we will be using very notations very heavily in the rest of the course in terms of proofs and all. So random variable will denote it as just a capital X, for example, and it can take any values, like let's say A, B, C, and this small x actually denotes this values. And that basically means that the probability that the random variable capital X takes a value equal to A, B, or X. And similarly for sample space also, the space we have already discussed is the space of all possible outcomes. It may be discrete space, like just a set of events. It can be continuous. It can be like a real number set, for example, or it can be even a mix of both. And so we now come to the definition of probability density function. And so what does it do actually? So I have a sample space S, for example, and let's say I have elements in that sample space, it actually assigns a particular number. So my p of x, you can think of it as a function, and x belongs to this sample space S. So actually, sorry. So x can be even like a subset of S. So I should write the notation accordingly. So and x can actually take a particular value, and that value is I can sort of govern. It can like p of x equal to some value x1 can be some uh, value in R, like obviously it's between 0 and 1, but that's the notion that I'm trying to suggest here. Is you can think of it as a function, and obviously it sums to 1, and that's the general notion, like of probability basic structure. And the notation wise, from now on, what we would do is like PR would actually denote a probability of an event. F would denote the cumulative distributed distribution function. Small p would denote the PDF or the probability mass function, and in case of like PDF, like if we have a continuous random variable, we just use PDF and PMF for discrete random variable. So that's the notion that we would be using from now on. So I'm just giving an example first here. So let's say you have a part of speech application, and you are given a set of words here, like as follows: the words in a sentence, and you want to map these words to particular part of speech tags. So the can be mapped to determinant or det. Plates can be mapped to noun. Clear can be mapped to verb. Similarly for preposition and all. And so we have a set of n words. So S is the set here, and so I have the weighted and all, and this cardinality is n here. And I want to. My problem is I want to output the pos tag for each word in S. So um, now I come with a question here. So let's say I assume like picking of words is done independently from the set S. I pick word one or word two, and this thing can be done independently of each other. So we want to find the probability that the new set, for example, I select um, from S, I actually select a subset, let's say S hat from S. So the S hat would actually contain some words in it. So if I go back to the example, it would be something like, um, yeah, it would be something like uh, let's say I only pick waiter and cleared and the and plates. So these things can be thought of as like S hat. And what I want to do is I want to find the um, I want to find the um, whether the words in that set S actually contains a noun, given that it already has a verb in the set S. So that's my like sort of problem that I want to, that's sort of the probability that I want to calculate. So I can go as follows. Let's say I that the word in S hat, a particular word W in S hat is of part of speech type, let's say K, and K can be anything, like it can be det or it can be prep or verb. So it's a discrete, like and it has a fixed size. So I denote it as I think it should be let's say PK, P subscript K, and let AK be the probability that the particular set S hat contains like a POS type K. So I want to calculate first probability of AK. That means the probability that the set S dash actually contains a POS tag of type K. So it can be calculated in the following way. So let's say S hat has like S hat. So this quantity actually means like nothing 1 minus pk is the k. So by the law of like sort of inclusion, I can say like if I don't include any word of type k in the set s hat, and on top of that I again subtract one, that itself would mean like my set s dash, this thing would actually just that ak would actually contain at least one element. And like, so again, the same notion that I've mentioned, like 1 speaker basically means that the word is okay, and since these are all independents, I just do multiplication over all the n pick from s, like s as n words, and them are not of type k. And so now the objective is to find this, like the a particular word that the set contains a word which is noun, given that it already has a verb. So again, applying Bayes' theorem, I can say it like this, and if I just expand it, so I have skipped a step here. So it can be like P of AK1 union AK2, sorry, AK2 is basically of P of AK1 plus P of AK2 minus P of AK1 union IK2. And so this thing can be is given by this itself. P of K comes in. And similarly, there is another one minus this thing. And for this thing is basically this thing plus one minus thing. So this thing cancel out. So one cancel out, and you are finally left with this expression itself. And that's the notion. And similarly, I just replace it for like k1 is noun here, k2 is verb here, and I get the final answer as follows. So this example actually applies the Bayes theorem in itself, and we just saw like one example of that. So I'll not go into any further like examples much, because it's already like something you've all seen. So I'll now go to the distribution functions notion of it. Like for example, the probability mass function. What exactly we mean by that? So it means like p of xa basically means the p of x is let's say a function. You can also denote it as p of x, and x is actually a capital X here. So and so that basically means like let's say probability of x equal to a, I can denote it as p of x a. So the probability that the event x actually takes on value a, or the random variable x is actually takes on value a, is basically the I can call it as a PMF as a function sort of. And for PDF, what do we mean by that? In PDF, probability density function, we for a continuous variable is a function that can describe the sort of like the likelihood relative for the particular random variable to occur. So it's basically, let's say I have domain D, and my random variable belongs to that domain D. So it's basically an integration of within the bounds of domain D and the probability distribution, like the PMF PX. So that's the thing, and for cumulative distribution, it's again like for I have two notions again here for discrete and continuous. So it basically means, let's say I have let's say my random variable x actually takes on values from like 0 to infinity, for example, and a lies somewhere between here. So f of a is basically all the probability of all values of random variable x less than equal to a. So the entire region here can be in the probability mass function can be thought of the cumulative distribution function. Similarly, for continuous variable, it can be, so here it's a minus infinity, considering my random variable lies from minus infinity to infinity instead of zero. So it's a integration or summation of all in summation in the sense of discrete variable from minus infinity to a. And you can, it's quite easy to see, like you can actually get back the sort of a PDF of the continuous distribution by just differentiating the CDF, because it's just an integration where you are applying it. So a sort of differentiation of this entire thing actually gives me back the sort of um my the PDF itself. So, and again, for similar notion we have for joint distribution also, like for let's say I have two variables, like I define a probability over two variables x and y, and like capital X and capital Y, and it takes on well, let's say I want to calculate the cumulative distribution such that X is less than equal to A and Y less than equal to B, and so it's a joint. Hence, I can just define it as follows, as a double integral over the joint distribution of P of X comma Y, and ranges from minus infinity to A and minus infinity to B for let's assume X ranges from when takes values from minus infinity to some upper bound. Similarly for Y, minus infinity to some upper bound. And again, if I want to get back the PDF here, I would have to do double partial derivative because it's easy to see also again, like since we have a double integration here. And in the case of a discrete notion, it's also similar. The integrals are just the analogous version of it is also summation operator, and it ranges from I sum it up for all x and y values up till a and b respectively. So now I'll just go through again, like I would come back to marginalization again. So because we will be using a lot of marginalization in PGN's probabilistic graphical models and all. So we saw some part of it in the Bayes theorem. We'll just go through more detail here. So marginal probability is basically the unconditional probability P of A of the event A, regardless of whether we had occurred or not. So that means, let's say I have an event A and event B, and that these are the only two events in my sample space, and I want to calculate P of A only. So in order to get this thing, I know things about the joint distribution, but I don't know the individual event probabilities. So how do I get this thing? So this is my known, and this is unknown. So I can just sum over all the B's here, and event B. So there is one event B, but there might be multiple such event B's, and I can just sum over them to get the probability of that particular event. So that's the notion. So I'm skipping some of it here. So similarly, this can be easy to verify also. You can also draw a Venn diagram to verify this thing. So yeah, so the other thing is for a discrete case that I showed you here is basically if the probability of x equal to a is basically probability the joint distribution of p where x takes value a, and I sum it over all values of my y. So p of x equal to a is basically summation of p of x equal to a y equal to y, and so I can write it something like this. And this can be, again, this is basically this only. So this, so that's it. And similarly for continuous case also, like the summation operator gets replaced by the integration operator, and we have the same notion. And so now we come to a small example, let's say I have like two independent continuous random variables x and y with same density functions. I want to find the density of x by y. So it's given by as follows: so e to the power minus x for all x greater than equal to 0 and 0 otherwise. Again, if you just do a summation of p of x, you can just verify it's comes out to be 1, and it's always positive. So it's a valid probability distribution. Um, and Now I have to find the density of x by y, and it's easy to check here. Like how I do it is like we first calculate the cumulative distribution, which is given by as follows: x by y less than equal to a, and this part of x by y less than equal to a is basically, if I can write it as like um, p of x comma y dx dy, and since y equal to a is in the denominator, I can put it up at the numerator on the other side of the fraction, and I can get the limit as follows for this. And for x, I sum it up from 0 to infinity, because e to the power minus x is like my probability is defined starting from 0, and it's 0 otherwise. So I you can solve it and find an expression like this. Now now we know this distribution function. We want to find the probability PDF itself. How do we do that? We can just do a sort of like a derivative of f, and we can get the PDF itself. And so we need to do the derivative at the point of A itself, like because we want to find the density up till that point. So if you do that, it's really simple to see, like we get something of an expression like this. And yeah, so these are like some examples, use cases you can try on to see to get an understanding of it. So now we go to conditional density. Suppose I have two random variables x and y, and we can define the conditional probability density of x given y as this. And so x by is so if I want to find what this means, so it's actually the same as writing this x itself. Um, So this is small x, for example, and this is the same as this. So I'll just use a division sort of operator, but it basically means this conditional probability. So capital X given equal to x, small x, and y equal to small y. And so that basically means is I can write it as follows. Again, like p of x is a joint probability by Bayes theorem, and similarly for continuous case, if I have, and in that case also, like I can write it as a joint distribution p of xy given x by y, as we saw in the last use case, and p of y, and this I can again marginalize with respect to x. So minus infinity to infinity p of x comma y. So that's what we have seen for the marginalization perspective. And so yeah, so this is just like the case for joint probability distribution and its counterpart in conditional probability distribution. And now we go through some of the basic rules, like sum rule and product chain rule, that we will be using heavily during the probabilistic graphical models course part. So marginalization, as we saw, like is just we can find p of x by just marginalizing over all values of y. And similarly, if we have more than two events, not just x and y, if we have n events, for example, and we want to find the probability density for x1, you can just marginalize over other variables x2, x3 up till x1, xn. So I have this entire thing. I want this probability only. I can just marginalize over the entire thing. And the product chain rule is comes from the Bayes rule itself. And now the general notion is for, let's say, for n variables, how can we find this? So let's say I have so for two variables I have something like this. I can write x1 and then I can write p of x2 given x1. And let's say, so for three variables, for example, it's if I have like something like this, so I can write p of x1 comma x2 comma x3 comma x1. Now I can also divide like factorize this also, because this expression itself is a joint distribution given my uh, given x1. So I can write something like x2 um, given x1. So it would be like x2 given p of x2 x3 given x1 x2. So um, that's way like so I now have, let me rewrite this thing. So now I have p of x2 given x1 and p of x3 given x1 x2. So if you generalize this for any random n, I can get sort of like a chain rule, and there is no independency conditions here, because if there was, then many of the factors won't be used, like the expression becomes much smaller. So there is a notion of tractable probability distribution. Um, in some cases, because might be too large and might be and in that case, computing each probability for each random variable, it's a tedious task, and it's in many cases it's not tractable. We'll look into those areas once we reach. So yeah, again, some concept of BS rule that we saw, like I'm just skipping it. And so now we saw independence of events. Now we have independence of random variables. So let's say x and y are two random variables, and this thing would again come into picture when we discuss probabilistic graphical models. So maybe I can just show a brief what I mean here. So let's say I can denote x and y as like nodes in a graph, and in probabilistic graphical models, what we do is basically let's say we have x1 up till xn events. So I can represent this entire distribution as a graph like this, and with edges basically meaning the relation between the events. So x1 and x2 are connected if x1 is not independent of x2. That means probability of x1 comma x2 is not equal to probability of x1 into x2. And that's the notion. But in this case, x and y, x given y, so it's basically probability of x into some, then it takes some value small x and probability of, and the same notion here that we have discussed right now. So similarly for also have the case for like random like for conditional independence also, like x and y are independent given z. So in a probabilistic graphical model structure, it would be something like z is my node in a graph, x and y are also node in a graph. So x and y are independent given z. That means it can have something like this. So x is actually dependent on z, y is also dependent on z, but given z, x and y are independent. And there are various examples. It can be something like, let's say, um, let's say some examples might be like X can be something like let's say getting a job, for example. Y can be like something like like getting a good grade in exam, for example. And Z can be like preparation, like some skills or preparation, for example. So given I have good preparation skills, I can get a good job, and I can also get a good grade in exam. But my grade in exam actually determine if I would get a good job. In some sense, it does, but I mean, for this context, it doesn't. Let's say like my job is independent of my mark sheet and all. I just get a job based upon what skill set I have learned. And so in that case, grading exam and job are independent of each other, given I already have prepared well. So the same structure I can write it as follows: like P of x comma y given z, and I can, as we saw in the last uh, to conditional independence. So now
Sir, you're not audible.
my voice audible now?
Yeah.
Rejoin me. Hello, am I audible?
Yes,
Hello.
sir. Yes, sir. You are audible.
Hello, is my voice audible now? Can anyone like write out or something if
You're audible, sir. Now.
okay. Yeah. Sorry for the issue. Let me start once more. Um, yeah, so let's say so we now were discussing about expectation. Expectation, let's say my capital X is a discrete random variable, and and uh, and it takes values x1 to lxn, and I can write just the expectation of x as as follows. Similarly, if I want to find expectation of f of x, for example, so actually this is a notation issue here. It should be f of x. So in that case, also I can would have something like this. And
Excuse me,
similarly for continuous case also,
the screen is
I just
different.
have x into px, and it's a integration over the entire variable range, and similarly for e of f
Sir,
of
your
x.
slides are
Pratik,
And
the
not
screen is
that's the
visible.
basic
different.
notion, and we would be using all again expectation in an upcoming class. So some of the properties of expectation is linearity of expectations. So that basically means, like, let's say I have two events x and y. I can just write it as follows: e of x plus y is basically e of x plus e of y. It's not hard to show, so I'll just suggest like you can go through it as part of like a exercise on your side, so that check like how you can like get through to it. And also there is another part, another sort of like small
Sir, you are not audible.
It's going on. Hello, is it audible? No. Good. So let me share my screen again. Just let me know once again, like if there is any issue like this, some network issues. Yeah, so we are discussing some properties of variance, and so variance of ax plus beta is basically it's got variance of x, and so you can check this. It's very simple to see. Like you can just instead of x, you would just have ax plus beta, and things would just cancel out, and yeah, and you would be left with this particular expression, and you can just check for yourself once. And so now we would go to the notion of covariance. What covariance means? Let's say again we have two random variables x and y, and covariance of x comma y is basically my the deviation from mean, sort of the deviation from mean for random variable x with the corresponding deviation from mean for random variable y. And again, if you expand this, you can get something like this expression. You can simplify it further. And so if my two random variables x and y are independent, that means the covariance is actually zero. It's quite intuitive because x and y shouldn't vary at the same time. It doesn't affect my varying in y. So if covariance of x comma y is zero, I can just write it simply as this. Again, if you see here, is again a product of two random variables in the expectation um, notion. It's a product of the two expectations. Similarly, some properties we have here for covariance, that things like covariance of x plus z comma y is basically covariance of x comma y plus covariance of z comma y. Again, these things I'm skipping now because it's easy to see. Like you can just write it down and check for yourself. And again, it's just going from the first principles. You can just apply this thing and you can achieve this result. So yes, so this is the covariance part. The other part is, I think, Chebyshev's inequality. I think after the probability part, I think I can directly go to the linear regression slides, and we can discuss that. I probably can keep linear algebra basics, I think, for next week, so that it because some of the things are mostly basic. I think many of you might know. So yeah, so I will conclude probability in a short while, and we can go on with linear regression after this. So Chebyshev's inequality. So basically says the following. So the probability that the deviation from the mean is actually greater than equal to some k. So let's say mu is my mean and x is a random variable. So this deviation is actually greater than equal to k, and the probability of it is actually upper bounded by some like constant, like, and that depends upon k itself. So it's less than equal to sigma squared by k squared. And again, it's very easy to show this. You can again go from the first principles to check, um, like in terms of how this thing expression comes up. And so what does this actually mean? So if my n tends to infinity, then the data would converge to mu. That means like n is basically all the values in x that x can take. And so that means if n tends to infinity, and the data would tend to, like, since this thing is actually upper bounded, that the deviation from the mean is actually upper bounded by some constant, it will converge to mu at some point. That means um, and that's actually the notion of weak law of large numbers. And similarly for other notion of it is, let's say if all my xi's are independent and identically sort of like distributed, then I can just write it like as follows, like this the if x1 I have x up till xn, and the mean of this samples only, and the entire mean of p of x, which is this part, this deviation again closes down to zero. Like the deviation that is greater than k is actually close to zero as n tends to infinity. And that basically means that mu and the entire sample space of like x1 plus up to x infinity, for example, let's say by infinity, is actually very close to mu. So that's the notion. And the next thing is some of the important classic random variables that many of us have already seen, and things that we'll be using in future are like Bernoulli random variables. What it's basically a discrete random variable, and it can take only two values, like 0 and 1. And so probability of xi equal to 0 is equal to, let's say xi equal to 1 is q, and probability of xi equal to 0 is equal to 1 minus q, because my summation is always equal to 1. So that's the thing. And if I just go to the expectation again, like expectation of x is basically summation of x comma p of x. So that means 0 into p of x equal to 0 plus 1 into p of x equal to 1. And if you just solve it, and it will be just the 1 minus q into 0 plus q into 1, which is this. Similarly, for variance also, you can just find it out, and it becomes something like this. So an example can be something like a coin toss example. Like a coin toss has only two like outputs, like head and tail, and in this case, it's always 50-50, so it's a 0.5 probability. Considering it's an unbiased coin, but there might be cases where it's a biased coin and probability of head might be, let's say, 0.4, and this can be 0.6. So something like this. It's an example of a Bernoulli random variable.
Hi Pratik, your voice is not audible.
Is it clear at the moment, or is it still? Hello, is it clear now? Okay. Okay,
Now
so
it's okay.
yeah, I think I changed my routers. I think some issues with that. So okay, let me open the my share my screen once again. Just a moment. So I think we can skip to linear regression. I think we have half an hour left. So we can skip to linear regression, and maybe we can again come back to this thing. So is my voice better than previous, or is it there is still some breaking and all? Hello. Hello.
Yeah, no issues.
Okay, okay. Thanks. Okay, so let me share my screen now, and let's see. Um, so we are actually starting with linear regression first, so that I think um, many like there is a lot of basic things that were going through. So you can just maybe ask me to stop anywhere. Like if you feel any difficulty, we can then go back to the basics once again. So so in ML, I think linear regression or regression in general is a very important topic. we were discussing yesterday in terms of supervised paradigm of learning. Their regression is like you want to predict the model wants to predict something, and the output should be a real value. And what is a linear regression? It's a very simple, but it's a powerful model. And so it provides interpretations of how inputs affects the final predicted outputs, and it can be applied to again to transformation of the inputs is also. And since it's a linear regression, but it also helps you to understand better non-linear models if you compare across towards non-linear models. So now the issue might be in data. Like data might have a lot of noise. Noise in the sense like data actually can come from a particular probability distribution, and with that probability distribution you can add some more noise to it, and it's it's very hard to know actually what is the true distribution of the data because of that noise. So data is information about the problem at hand in some quantized form, and it can be collected through various forms. It can be through like questionnaires, surveys, or measurements, for example in lab experiments, or sensor data, for example. And there is a lot of noise that can get added in this data. So measurements can also have human errors also that can be act as noise, and some measurements can be incomplete also. And so there is a lot of problem with noisy data, and that can affect the model predictions also. So an example of sort of 1D linear regression, so one dimensional linear regression is as follows. Let's say on the x-axis we have like the sort of like as the number of CPU cores. Let's say I start with one CPU core, two CPU core, up till 8 CPU core, and on the y-axis I have the corresponding prices. And the black dots in the graph actually means the price point for core CPU core number this. So for example, for CPU core number 4, its price is around 4 lakhs or something. And similarly as follows. Now I want to fit a line that actually generalizes across all these data points. Why do we need to fit a line? Because we want to, let's say for CPU core 10 CPU core, I don't have any data, but I want to extrapolate from the red line itself to know what possible prediction for the price would be. So I want to fit a line here, and that's the concept of linear regression. That you want to fit a line based upon the training data points, and there might be many possible fits also. There might be, I can have something like let's say this is one fit. I think I think it's not showing in the graph, but it can be like you can join all the points in a curved fashion, for example, and that can be another fit, for example, instead of a linear fit. And so how do you compare which fit is good for your data set? Like there might be multiple curve fitting, and you can define an error function. Let's say f comma d. D is my data set, and f is my sort of the function that actually it's like that actually takes the input from the data set and outputs a real number. So the regression function itself can be thought of as f. And I want to compare the error function. So error function in this thing would be something like, so my red line is actually the function f here, and all the black points are actually my data set capital D, and I want to calculate the error function. So one notion can be like I can calculate the distance of the red line from each of the data points, and like it can be like plus minus sort of um, like uh, like vertical distance of each of the points from the red line, and I can measure some sort of error across all the data points. How good is my curve fit? and I want to choose that particular curve for which my error is very minimal. And yeah, so that's my point. Like that's the point of here. So there are many notions of difference. One can be a simple, as I mentioned, like it can be as simple as a vertical difference, for example. So I have xi comma yi, which belongs to my data set D. F of xi is basically the red line at xi is actually my CPU core number. Let's say 4 is my CPU core number, and f of xi is 4 also. And yi is actually f of xi is actually 4 point some 4.23 or something, because the red line actually corresponds to something at here. And for my data point CPU core 4, my exact price value is 4 lakhs. So that 4.2 minus 4.2 is my error for that particular data point. So likewise, I sum it up for all my sort of data points. So the other notion can be of take a absolute value of the difference, not just any, because you you all might know this already know like why this is the case. Because if I don't take an absolute value, it might happen like some points lie above the red straight line, some points may lie below the red straight line, and that averaging thing might cancel out. Like there might be too many same number of plus ones and plus minus ones. It might cancel out to some very small number or zero, even zero. And if it's a very small number or close to zero, that doesn't mean that means actually the curve is a good fit because my average error is low. But that actually doesn't mean it's actually a good fit, because on an individual level there is a lot of loss of deviation. The deviation just cancel out. That's why the average on an average is comes out to be zero. So the in order to solve that issue, we can have an absolute sort of difference that actually doesn't cancel out this plus minus deviations. And the other notion can also be like a difference, a quadratic difference. Now I think like why should we go with the third option and not with the second option? And there are many like, I mean, we obviously do so we would be discussing the loss functions in some upcoming lectures, and there are many reasons for why some the third loss function might be suitable over the second loss function, or in many cases the second might be suitable over the third. And so we will discuss those things in detail. So now the fourth function can be, again, it has the same problem as the first one. So minus 1 whole cube is actually minus 1, and it again captures the minus negative into the summation, and it might again cancel out some parts of it. So this is not a good option. So there might be many more. So all even powers of this difference is actually a good estimate, like can be a good estimate of the curve fitting. All odd powers is not a good estimate. So that's the notion. And yeah, so it actually is quite a simple metric to give me a difference of a measurement of difference from the original value. And so one of the popular loss functions which I was mentioning is least square loss function. Least square um, or is in many cases it's also called L2 loss. L2 because it's in the L2 space I'm calculating this loss. So f of xi minus yi whole square, I sum it up over all data points, and the final thing that I get is my loss function, which is the least square loss function. And I can use this loss function for my regression problem, and it's one of the most popular loss functions used. And so my objective is to find a curve that actually minimizes this loss. So we always want to minimize the above function. And as you can see, it's quite easy to see. It's like it has a parabolic sort of structure, and it's continuous all throughout, and it's also differentiable everywhere. And why do we need a differentiability? Because obviously we are not discussing that here, but if you already know about neural networks and all, then there's this concept of backpropagation in neural networks, where you need to uh, by chain rule you need to uh, find a different, you want to differentiate the loss with respect to the model parameters. And for that reason, the loss should be differentiable in that sense. And so that is one of the reasons, this is why a popular loss function, because it satisfies all the properties. And it's also called a um, L2 loss, which I mentioned, because it can be thought of like a square of the Euclidean distance between predicted points and the actual points. So the Euclidean space is also known as the L2 space. So that's why it's called L2 loss. And similarly, the mathematical treatment of this function will be, I mean, it's quite intuitive. Many of the results are quite like sort of gets quite relaxed once you use this loss function. So we'll see further once we have some proofs and all. So we now go through some basic notation. For example, my dataset D has x1, y1 up till xn, yn, and while x1 to xn on my feature points or input variables, yi or yj are basically the output of the dependent variables. And for the jth training example, I can just have something like xj, yj. It's my jth training example, and the total cardinality of the set D, like the number of training examples, is n here. And for the d-dimensional data, I have like, let's say, d-dimensional in the sense like each of my data points, xj, each of my input variables xj has dimension d. So that means I can take, like, you can think of each of xj as a rectangle of d, um, d values. um, and in that sense, if I go to the matrix notation here, um, that basically means, so row wise I have n instances, so that's why I have x11 to till xn1, and column wise I have d dimension for each input, so that would be x11 to till x1d. Similarly, for my output y, which is my the labels of my data set, it's also of dimension n, because I have n training instances. So now, with this notation that we discussed now, we would be using this notation throughout now for the time being. So we now want to find out um, uh, the loss objective for a general regression problem. Let's say, f is my curve, like f is the function, and the red line that you saw in this example, f is my red line, and this is one of the curves that I want to output. And there might be many curves, as we discussed. And we want to find the best optimal curve that actually fits the data, training data. And so my objective is, like, I want to minimize the error function between f and d over all possible sets of curves or functions in the space f. So the capital F denotes the class of functions over which my error minimization can be performed. And I take an arc mean of it, like a argument mean, and that actually gives me the optimal curve or the optimal function f star that actually fits through all the training data points. And so in case of, so this is my general regression problem at the top. Now we come with the notion of parameterized regression problem. So this function f can be thought is actually a function of x initially, what we saw, like here this function f is actually a function of the input variables x. Now there can be other um, parameters also in this function, like w for example. And w can be thought of like the model weights. For example, in neural networks you have weights in between two layers, weight vectors between two layers. So w can be thought of some parameters, extra parameters that the function needs apart from the input variables x. And what we now want is, we want to actually find the optimal parameter w that actually minimizes the loss instead of f star. So changing w actually changes f. You can think of w as a knob, sort of switch or a knob, and you keep on changing it. My the entire f of x comma w actually changes structure. It can be f can be at one time for a particular w, f can be like, let's say y equal to x, or for the particular w, f can be equal to y equal to 4x plus something. So something like that. So w is something like you change like a knob, and you minimize again the error function with respect to w, and you find the final optimal w that minimizes across all the space of all model parameters. So in the case of linear functions, in linear regression, for example, so we discussed generalized regression. It's not linear regression, but it's a generalized version of regression. Now we come to linear regression, where this function f can be only linear functions. It cannot be like any quadratic function or something. So in that case, my f of x of comma w can be can be thought of like w transpose x plus w 0. So x and w are actually both vectors, as we saw, and that's why it's a w transpose x, and w0 is a scalar. So this entire this entire product, if you call it, is actually a scalar. It's a one cross one element. And so this is my sort of the concept of linear regression. And why is it linear? Because it's linear in w. It's not linear in x. Like it should not be linear in x. So it can be like w transpose x squared plus w transpose plus some x w naught. It's still called a linear regression problem because it's linear in w. So that's the notion. And so regression is basically about learning to predict a set of output variables, which are my dependent variables based upon a function of a set of input variables or independent variables. And what is a prediction actually based upon? Prediction is based upon previous observations, like in the training data set. For example, you have a lot of training data set, and those observations actually can help you to predict for a new data point. So let's say company wants to determine how much it should spend on TV commercials to increase sales. So my sales value is actually my output variable y, and my uh, cost of money, like money or cost, is my input variables x. And so xi is basically instance of money spent on the advertisements, and yr is basically the corresponding sale figure. And I have historical training data or observations that if I spend this amount of money, I get this amount of sales. If I spend a larger amount of money, I get a good amount of sales. This historical data I have, and now I want to predict for the next, let's say, next year, or for example, the company wants to predict for the next year if they should spend this amount of money, and what is the expectation of the sales they should get. So that's a linear regression problem application in itself. So suppose you have so you want to so I'm showing this for a 1D one dimension input feature, because my x is basically a cost or a value, a real value money, like $100, $200, something like this. And my w1 is a weight variable, and w0 is also a sort of you can think of it as a um, like an extra bias sort of, like you add w0. And so my x star, which is the optimal value, which can be thought of like is the optimal value of y star minus w0 by w1, and it can be used to determine the value that I should spend. And this this estimation problem actually also would depend upon w0 and w1. What is the optimal value of w0 and w1? So we need to find those values w0 and w1, and from the by based upon minimizing the error loss on the previous observations. So you can think of it something like this, like I have previous observations like this, and I want to fit a straight line, sort of fit a line that can actually act as a predictor for future TV cells. And so we use a least square of the squared loss function, which we saw previously for endpoints, n training instances. I sum it over all the n instances. And if I do it for this particular problem, f of xj is basically my w0 x w0 x um, w0 into some is it's only w0 plus w1 into x11 x1d plus w. So if you just this particular expression, if you just expand, because x is actually this part, x is actually x1 up till x1d. The small x is actually x1 till x1d, and w is basically a column vector of w1 till wd. So if you just expand this, it would be fairly easy. So I'm not going through linear algebra basics in this lecture. Probably I might go through that next week. But it's I think probably most of you might know like what I'm trying to say here. So it's basically if you expand the dot product itself, like you can get an expression like this, and my objective now becomes something like this. And I now I want to find out the optimal value of the weight that actually minimizes this loss. And so it can be like thought of as a in a two-dimensional sort of scenario. We only saw one-dimensional scenario like this. In a two-dimensional scenario where we have it's like two-dimensional in the sense like in the input space I have two dimensions, x1 and x2. In that case I want to, instead of fitting a line, I want to now fit a plane. It becomes a 3D space once we include the output variable. So we want to, instead of fitting a line, now we now want to fit a plane upon the thing. So in higher dimensions you get obviously you can't visualize, but it's sort of like a plane in a higher dimension. So that's a notion. And so how do you sort of get this optimal value of w0 and w1? So I think probably this would take some time. I think we can conclude for today, because I can start from here, or maybe I can go from um, uh, linear algebra basics first. And yeah, I think that's the thing. So before I conclude, like, do you have any other questions or any questions from the topics that we discussed today? You can mention now. Yeah.
Sir, one thing I want to say is
Yeah.
that we don't have we only have guest access to Teams. So it would be better if you share the
Uh-huh.
presentations and slides in the groups.
Okay, okay. Oh, I see. So you after the, you mean slide presentation, the lecture slides or the?
No, whatever you want to share it in Teams, because
Uh-huh.
we cannot access them because we only have guest access.
Oh, I see. Actually, I think could have done it on my personal Gmail account, but in Gmail, I think they don't give you access to, on personal Microsoft account. You don't have option to create a MS Teams, like Teams tab sort of like where
I don't
the
think
similar.
so. No, I don't think so. It is a licensed software, I think.
Yeah, I think but for personal accounts they don't allow that.
No, no. You
I
need to
see.
have a
Okay.
Teams account. You need to have a
Yeah, yeah.
Teams account. So I think you can share it in the group that you have created.
Yeah, I have created a Google Groups, so I can share it there.
Yeah.
I will be talking with the coordinators at ISS. I'll just check with them if there is any option for them to sort of create an MS Teams account on that behalf and add us all there as a like an actual account there instead of guest. So yeah, I'll just check that. For the timing, I can share everything in Google Groups. Yeah. Yeah. Any other questions? Okay. I think we can then conclude for today, and we'll meet again next week. In the meantime, I will just share a form sort of for timings. Like when I think few of the participants have already requested some change in timings and all, so I will just float a form for voting to see. And yeah, I will just keep you updated if there is anything, and we can meet again next week. So yeah, thanks again for joining today, and